Dear students, so welcome to another lecture of microcontrollers. So in the last lecture we were going through the basics of a microcontroller, and we were talking about a hypothetical microcontroller with very few instructions, and then we saw how we can write those instructions and command the microcontroller to perform some tasks. We saw that those instructions had opcode and an operand, and how those instructions were converted to um, hexadecimal formats and were stored in the memory, and one by one those instructions would be performed um, by the microcontroller, incrementing the program counter. Okay, so today we will be a little more specific, and we will talk about the 8051 microcontroller, and we'll see how what we introduced in the last class is applicable here also. Okay, so let's start. To begin with a bit of history, so the 8051 microcontroller was developed by Intel in 1981, and it was initially an 8-bit microcontroller, and it had the following specs: so 128 bytes of RAM, 4 KB of on-chip ROM, 4 general purpose input output ports, and each of those ports had 8 pins, so there were 32 pins. Two 16-bit timers and counters, one serial port, and one on-chip clock oscillator. So we will get to know about the details of these as we proceed through this module, and you will see in this lecture and the future lectures what are the functions of these things, and how they perform. So So 8051, it became very popular after Intel allowed other manufacturers to make different versions of 8051. So Intel didn't keep it a complete proprietary thing. Okay, it was allowed to manufactured by other manufacturers. Okay, uh, but there was a condition provided that the code compatibility was maintained with the original. Okay, so this has led to many versions of 8051 with different speeds, different amounts of RAM, but since they are all code compatible, if you write a code for one of them, it will run for the other chips as well, and this is what you will exactly do in your labs. So in your labs you will be using a chip that is manufactured by a different manufacturer called Scilab. Okay, so but then what you are learning in this module, most of the theory applied to that chip, and most of the code, assembly language code that you will learn to write will be applicable there. There will be few things different in the architecture of that chip that you are using for your labs. So we will explain those and get into those differences later when you start doing your labs. So the 8051 is the original member of the MCS 51 family. Other members of this family are 8052, which has more RAM, and 8031, which has no ROM. So generally we will focus on the 8051 for this course, but later on, towards the end of this semester, when we will do interfacing with external devices, you will also get to know a little bit about these two. Okay, so so let's move on. So this is the schematic architecture of the 8051. So you see we have an address bus of 16-bit, We have internal memory. Okay, so this is the internal RAM, then the general purpose register, stack, then the bit addressable areas, and the special function register. So we will also explain each of these in detail uh, as we proceed. Then we have the internal bus that connects with your external data bus, that is 8-bit. Okay, and the internal bus, as you can see, is passing data from one internal block to another. Okay, so for example, we have this internal memory, then data can be exchanged between this and, let's say, the program counter here using the internal bus. You also have another special function register called dptr. Then you have the arithmetic and the logic unit, which is also an 8-bit unit, and that does all your arithmetic and logical operations. You have a temporary register where you store your data temporarily to be operated on by the ALU. You have the accumulator, which is used for most arithmetic and logic operations, and the final results are stored in the accumulator. Sometimes the final results are also stored in the B register. You have the instruction register and the instruction decoder. So these are the dictionary of the microcontroller, as you learned in the last class. They decode the different instructions and then converts them to machine level or assembly level language for the microcontroller to operate. You have a set of flags that is contained within the program status word register. Okay, so these are like carry, auxiliary carry, overflow, and parity, etc. We will also learn the functionalities of each of these flags later. And then you have the control lines. Okay, so for sending control signals to the different units. Okay, so so we talked about the internal blocks of the microcontroller, and then sometimes the internal RAM may not be enough, so you can interface with external memory. So you have external data memory and external code memory. So you can store your code also in an external memory, and then using the combination of the data bus and the address bus, you can access these codes. You can access also data from the external memory, and with the combination of all these buses and the control lines, the whole thing functions as a combined unit. Okay, so these things, this external memory interfacing, we will do in a full detailed lecture towards the end of this semester. So Intel actually developed this 8051 microcontroller way back in 1981, and some of the latest Intel processors are the Pentium family of processors. Okay, Intel has developed even faster and even more sophisticated chips now, but Pentium was one of their very popular chips until a decade ago, maybe. So let's compare the Pentium processors with the current microcontroller that you are studying. Okay, the idea is to just compare the 8051, which is a very basic computer, mini computer, with some of the latest chips that we have. Okay, so Pentium chip, first of all, it has a 32-bit ALU. So you saw that your 8051 had a 8-bit ALU. Okay, so that's 4 times speed up. Okay, then the data bus is 64-bit, as compared to 8-bit in 8051. The address bus is 32-bit as compared to 16-bit in 8051. So there quite a bit of scale up both in terms of addressing and data. And then the Pentium's memory space is external. Okay, so let's see in this table the exact differences. So first of all, the clock speed in 8051 is 12 megahertz. Some 60 megahertz ICs are also available, but Pentium is 1000 megahertz or 1 gigahertz. Address bus, as you saw, 16 versus 32, data 8 versus 64, ALU width 8 for 8051, 32 for Pentium. Applications wise are both these chips are also different. So 8051 is mostly used in domestic appliances, peripherals and automotives. Pentium is used for personal computers and other high performance applications. Power consumption wise, 8051 is a very low power device, small fraction of a watt is used. Pentium uses a little higher, tens of watts. And then the cost of the chip, okay, so 8051 is very cheap, okay, about the order of 20 RMB, okay, and Pentium costs are higher, about this much, but then it varies depending on the specs. So so let us focus more on the 8051. Let's see the memory representation in more detail. So this is the internal memory as you saw, and then it has the internal RAM and the internal special function registers. And then you can interface them with external code memory and external data memory. So up to 64 KB of ROM and up to 64 KB of RAM. Okay, so this comes directly from the fact that you have a 16-bit address bus. So therefore you can address up to 2 to the power 16 addresses, and that is basically 64 KB. Okay, so so in the 8051's on-chip memory there are 256 memory bytes, and the first 128 bytes are reserved for register banks, bit-addressable RAM and general purpose RAM. And then the next 128 bytes are your special function registers. Okay, so and these are the ranges again of the register banks. So this is the starting address, let's say 00 hex to 1F hex. So there are 32 register banks. Then you have the next space is for the bit addressable RAM from 20H to 2FH, and then the general purpose RAM from 30 to 7F. Okay, this is H. And then these are the special function registers. Okay, so so here it's shown in a more zoomed out fashion. So from 00 hex to 1F hex you have all the 32 register banks. Okay, so there are 4 register banks. Okay, 2 and 3, and you have 8 registers per register bank. So total space is 32 from 00 hex to 1F hex. Okay, then from 20 hex to 2F hex you have this bit addressable memory area, and each individual bit within the area can be accessible separately. You can add a bit and you can delete a bit individually from this area. So that's why it's called bit addressable. And then this is the general purpose RAM of 80 bytes. Okay, so So altogether from here to here is your internal RAM, okay, and then that makes 128 MB, okay, and then this part, the remaining 128, is the special function registers, okay. So let's go into a little bit of details for the bit addressable RAM part. So 8051 supports a special feature which allows access to bit variables, okay. So this is where individual memory bits in the internal RAM can be set or cleared, and in all there are 128 bits numbered between 00H to 7FH, okay. That's the total, RAM area. That's the bit addressable area. So these are the total number of bits that you can address. Being bit variables, any one variable can have a value 0 or 1, okay. So a bit variable can be set with a command such as setb and can be cleared with the command clear, okay. So these are the example instructions. So you can say setb 25H, okay. So this sets the bit 25H. Then you can clear the same bit. This clears the bit 25H and it becomes 0. Okay, so there is an important note here. So this bit 25H is actually bit B5 of internal RAM location 24H. So let me go back and explain that to you. So we were setting the bit 25H, okay, and then we were clearing that bit also. So let's see what is 25H. And when you are using set and clear, this means you are actually operating in the bit addressable area, because these are operating on individual bits, okay. So let's say 25H, okay. So you have to count from here. So these are the individual bits, okay. So you see the numbers here, they represent the entire blocks, okay. So let's say this entire block is represented by 2DH, okay. Or let's get from the start. So this entire starting block of the bit addressable area, which has total 8 bits, this is referred as 28. So these numbers are coming from the addressing of the total total internal RAM of the microcontroller, that starts from 00 and ends at 7F, okay. But then the bit addressable area starts from 20H and ends in 2FH, okay. Within this area, each of these 8-bit blocks have a address. So this block is 2FH, this block is 2EH, this block, as I highlighted before, is 2DH, okay. But then inside these blocks there are individual bits which are numbered like this. So it starts from 00, the LSB of the bit first LSB of the bit addressable area starts from 00, then it is 07. So these are the first 8 bits corresponding to this addressing byte 20H, then 08 to 0F, and so on. So we were working with 25H in our example. So 25H is basically somewhere here, okay, because this is 20 to 27, okay. So this starts from 20, 21, 22, etc. and 25H will be somewhere here, okay. So this is basically the bit B5, okay. This is basically the bit B5 of the bit addressable area 24H, okay. So this is what I was saying here, in this note. So bit 25H is actually bit B5 of internal RAM location 24H. So this is something which you should remember and not get confused. The bit addressable area of the RAM is just 16 bytes of internal RAM located between 20H and 2FH, which I just said. So if a program writes a byte to location 20H, for example, it writes 8 bit variables, bit 00 to 07 at once. Okay. So moving on with the registers, so the CPU has direct access to several 8-bit registers which are located in the RAM block. So you saw there are this A and B which are associated with the arithmetic and logic operations, but then there are these 8 registers R0 to R7, and these are used frequently for storing bits on which arithmetic operations will be done or logical operations will be done. So the A register is also known as accumulator. It is used for all arithmetic and logic operations, and then you have these registers. So there are R0 to R7 in each of the 4 register banks, and you can use them for temporary data storage and then doing some arithmetic and logical operations where the final results will be stored in A and B. Okay, so let's see. But before that, let's have a quick look into the special function registers. So these are all the special function register, and as you saw in the last slide, accumulator or the A register and B, they are also a part of the special function registers. And then there are many more which lies in this memory location of the internal memory, and we will go through each of the special function registers when we study in detail the future related topics. For example, when we will study timers, we will study this register TH1, TH0, TL1, TL0, Tmod and Tcon. Okay, so these are all related to timer operations. When we will study, let's say, serial communication, we will study SB, UF and SCON and etc. When we study interrupts, we will study IP and IE and so on. So we will get to the details of these registers later when we will study related topics. So let's move on with the basic instructions to get you familiarized with the functions of the registers R0 to R7 and A and B. So let's start with move. Okay, so move is an instruction that copies data from one location to another. So it has the following syntax: move followed by the destination and the source. Okay, so the destination in this example is, let's say, the A register, and the source is this data. Okay, so whenever we are using this symbol, okay, this symbol tells the assembler that this is a value and this is a number and not another register. Okay, for example, so this is a direct number which is 55 in hex format that you are moving to the A register. Okay, so this is known as immediate addressing. We will also study this later in detail when we do addressing modes. But yeah, so this is the syntax of move. You have a destination, that this is a register in this example, which is the A register, and the source can be another register or a direct data. Okay, so you can either move the contents of another register to register A. Okay, you can write move, let's say A, and then let's say R0. So in this case you are moving the contents of R0 to A, but in this case you are moving directly a number which is 55 in hex to A. Okay, and to denote that we use this symbol here. Okay, so with the register A loaded with the value, we can perform further move operations. For example, you can move the contents of A to the register R0. Okay, and you see we have written comments here, so when you will be writing assembly codes, you can write comments by using a semicolon like this. Okay. Then let's take another example. So we are moving this hex value, which is a data denoted by this symbol, to register R1. Okay, and notice that here we put a 0 in front of the hex value, and this informs the assembler that the F represents a number rather than a letter. Okay, now if you write like this, then this will cause an error. So whenever you have a hex number that has a letter at the leftmost place, then you precede it with a 0. Okay, otherwise there will be an error. So now we can have an add instruction. So this tells the CPU to add a given number to the number currently in register A. Okay, so it has the following instruction. So add instruction always comes with this accumulator. Okay, so add A and then the source. Okay, so this source can be just a number. Okay, or it can be the content of another register. So here in this example you are saying move A 25H, so you are moving this number to the accumulator, and then you are using add instruction to add this number to this number. So when, let's say, you need to add two numbers, okay, so you move the first number to the accumulator, and then you use the add instruction to add the next number to the contents of the accumulator, which is 25H, after you execute this instruction. Okay, so alternatively we could have moved each of these numbers into a register and then added each of these registers to the accumulator in turn. So you can write, you could have also run written your code like this. Let's say move R0, you are moving in register R0 this number 25H, and then you move to another register R1, let's say, the other number, which is this. Notice how I use a 0 here, because the leftmost is an alphabet. Okay, and then you can do add A R0, and then you can add A R1. Okay, so after this line you assume that your A is cleared, or your A has value 0. Okay, so after this line basically it is adding the number the 25H, which was in R0, to A. Okay, so A will now have, after this line, 0 plus 25H, whatever, and then after this line it will have, A will have 25H plus 0A 3H. Okay, so you can write this also like this. Okay, they are equivalent. So so this is what I just told you. Okay, so it is important that you write this line in between, so that your accumulator contains 0, and then you can do all this. Okay, what I just wrote in the previous slide. So your add instruction must be used with accumulator. You cannot you cannot do this. Okay, you move the number 25 to R0. This is okay, and then you cannot directly add the other number to the contents of R0. This is not okay. So you have to do addition using the accumulator. So you need to make an adjustment so that you can add only using the accumulator. So that's why you are moving the two numbers into two registers and then adding them separately to the accumulator, because add instruction can only be used with the accumulator. So let's do a class exercise. So write the instruction to add the values 16H and CDH and place the result in register 6. So what is the sum? So you can just look into this code and then try to draw inspiration from it to write down your code for this particular exercise. So you can move R0 with, let's say, 16H. You can move your A with CDH, and then you can add A with R0. So A already has this number. You are just adding this number which is in R0 by writing this, and then after this line your accumulator A will basically have A plus R0 or basically CDH plus 16H. Okay, so A will contain this addition whatever it is. So you have to move the result in register 6. So the final line will be move to R6 the contents of A. So I leave it to you as an exercise to find out what will be the sum. Okay. So moving on, in general an 8051 assembly language instruction is divided into the following columns. So you have, what is opcode and operand from your last class. So these will be there. There can be a comment followed by a semicolon, and then there can be a label also. Okay, so you can label a line so that you can jump to that label if you need to in your program. Okay, so what does that mean? So let's say you can label this line as loop. Okay, so basically this line, what it is doing is adding the contents of register 1 to register A or the accumulator, and then you want to keep doing it. Okay, so you use an instruction called sjump or short jump, sjmp, and then you keep doing this. Okay, you keep jumping to this line and then you add again, and then come here, and then again you jump here, and this is a loop that you can run. Okay, so that's why you can use some labels to just jump to those lines. Okay, so the general instruction format is label, opcode, operand, and then comment. So these are the steps of writing and running an assembly program. So you can write in any text editor and save the file as .asm or .src, and then feed the ASM file to the assembler and get an object file with an extension .obj and a listing file with an extension .lst. Then a linker program links the object file with other required object files and creates an absolute object file with extension .abs. And then the last step is the OH program creates a hex file from the .abs file. So we can burn the hex file into the microcontroller's ROM, and then it can start executing the instruction that you wrote in the code. So the list file is a useful one for the programmer because it shows all the opcodes and addresses. So you will be more familiar with these steps when you will be writing codes for your labs. Okay. So moving on to data types and directives. So the 8051 family has only one data type, which is 8 bits. Okay. And then you have this different directives. So the first one is DB, which means define byte. So whether it's an integer, whether it's a decimal or a binary or a hex or ASCII format, you can use this DB to define the data formats. Okay. So org you came to know in the previous lecture. So basically this is suggesting the origin of the code, and this is used to show the beginning of the address. So in the list file, the code after org are put at the location in ROM that starts from this given address. So let's see. So you have org here. So this is the address from where the code actually starts. So this is the origin of the code. And then you have these different data. So you can define a decimal number by using db28. Okay, nothing is mentioned here. That means this is decimal. You can define a binary number by putting a B at the end. You can define the data type hex by putting H. And then you can also define ASCII by using these inverted quotes. You can define ASCII strings larger than 2 characters like this. And everywhere you are using this DB, which is the directive for define byte. Then you can have this equate directive. This is for the comfort of the programmer. So it is used to define a constant. So you can define a constant like, let's say, count, which is equal to 25, and then you can use multiple times these constants. So you can use it in your code. So if you're writing a large code, then this is a good practice to define some constants at the beginning and then use them in the code. Okay. And then this end directive, this shows the end of the program. So the assembler considers end as the last line of the program in the source file and ignores anything after that. So this is important. Okay. So when you're writing a code, don't forget to put your end. And if you write anything after the end, or if you mistakenly put the ends before a line, then that line will not be executed. So let's look into the jump instructions and the loops. Okay. So you saw the use of labels to use the jump instruction. So basically, in any high-level language like C, so loops are one of the most widely used instruction. Okay. And in a microprocessor also, we can use loops by using this type of instruction. So you can use a label for a particular line, and then you can have a register, any register. Let's say R0, R1, whatever, like up to R7. And then this instruction DJNZ means decrement and jump if non-zero. Okay. So let's see an example to see how this can be used. So let's say you are supposed to write a program that clears the accumulator, then adds the number 3 in decimal to the accumulator 7 times. Okay. So let's say clearing the accumulator is done by this instruction. So we are basically moving a 0 directly to the accumulator and it's cleared. And then you are moving the number 7 to R0 because this is the counter. Okay. So these many times you have to run your loop, or you have to repeat the addition operation. Okay. So now you are adding this number to A, and this is 1 times. Okay. and then you use this DJNZ R0 followed by this level. So what this line is doing, it's decrementing R0. So R0 is 7. Okay. So DJNZ, once this line is run, it's decrementing R0 to 6. Okay. And jump if non-zero. So 6 is not 0. Okay. 6 is not equal to 0. So it will jump to this line. Okay, and then add 3 again, and then it comes to this line again. R0 is decremented to 5 and it's still not 0, so it will again jump to this line and then again add. Okay, and it comes to this line again, and this loop will run until R0 reach to 0. Okay, so it will keep decrementing. When R0 is 0, it will not jump again to this line. Okay, so in that way you are adding 3 to the accumulator 7 times, because this loop is running up to the value of R0, which is 7, as you have loaded it previously. So you will see that the final outcome will be 21 in decimal or 15 hex, and that will be the result stored in the accumulator. And the register in the DJNZ instruction can be any of the registers, R0 to R7. You can choose anything according to your will. So now the question is, what is the maximum amount of times the loop in the previous example can be executed? Okay. So since R0 is an 8-bit register, the maximum value it can store is 255. Okay. So therefore the loop can be executed a maximum of 255 times, because the maximum value that you can load here, instead of 7, let's say, you can load 255, and that is the maximum that you can load. And then when you are writing DJNZ R0, this line can be looped maximum 255 times. So what if we need more than that? How can we perform a loop more than 255 times? And the answer is, you can use nested loops. Okay, so nested loops, so you can write nested loops in high level languages like C. Okay, so you have nested for loops. So for I equal to 1, I less than equal to 10, let's say, and then I plus plus, you write like this. And then another loop you can write for j equal to 1. So this is an example of a nested loop. J less than equal to 20, let's say, and then j plus plus, you can do something with I and j. Okay, so so something to do with I and j inside this loop, and then you end. Okay, this loop and then end the other. Okay, so so you can similarly use nested loops in assembly language. So let's do an exercise and see how it works. So write a program that clears the accumulator, then adds the number 2 in decimal to it 500 times. So this is more than 255. Okay, this is, so we have to use a nested loop here. So what is the final value stored in the accumulator? All right, so we can write the code like this. You can split 500 into 2 factors. So here we have done 5 and 100. You can do 50 and 10, whatever. You can also do 2 and 250, as long as these are less than 255. Okay, so you can choose any number. So 5 and 100, let's say. So you have first cleared the accumulator and then moved 5 to one register and 100 to another register, and then you are doing the addition. Okay, so you add the first addition, and then DJNZ R1 loop inner means that it will go here. Okay, so R1 has 100. Okay, so this inner loop will run 100 times. okay, and it will add 2 to the accumulator 100 times, okay. Then comes the outer loop. So when this register R1 is 0, it will no longer repeat this step, okay. This will go to the next line here, and then R0 is 5, so it will go to this line. And what this line is doing is reloading R1 again with 100. Okay, and then it goes to the next line of the addition, and then it will run the inner loop, okay. So the first 100 additions will be done, then R0 is 5, so it is not 0, so it will go to this line, and then R1 will be reloaded with 100, and then the next 100 additions will be done, and then again it will go here, okay. R0 is 3 now, okay, so it will again go here, and again the R1 will be reloaded, and it will do the next 100 additions, okay, and it will come here. R0 will be 2 now, it will go again until R0 is 0. From 5 it will keep reloading R1 and keep doing the addition. So R0 is taking care of the outer loop, and R1 is taking care of the inner loop, okay. So so this is how this works, okay. Or in other words, let's say when your R0 is 5, okay, your R1 is decremented 100 times, and this implies that you add 200 times. Then when your R0 is 4, after it has decremented one place, you again reload R1, and then the same operation happens. So you add 200 times again. So in this way, as long as R0 goes to 0, you keep doing these additions 100 times, 100 times, 100 times up to 500 times. So when your R0 is 1, the final 100 times occurs, and then when it becomes 0, it stops, okay. So this is the logic and the algorithm. So this explains what I just said actually. So and the final value in register A will be 2 times 500. So 500 is sorry 2 is added 500 times. So 2 times 500 is 1000. But then since whenever the register reaches 255, it overflows. So you have to do this operation 1000 mod 256, and then the final value will be 232 or E8x. Okay, so every time it overflows after it reaches 255, so it starts from 0 again. So you have to do this operation to find out the final value. Okay. So there are other conditional jump instructions, for example, jump on 0, okay, which will jump to this level provided the accumulator is 0. And then we can have JNZ, which will jump to this level provided the accumulator is not 0. Okay, so there are different conditional jumps, and you can use them in a program. So for example, write a program which determines if register R1 is 0, and if it is, then load it with the decimal number 10. So you move the contents of R1 to accumulator, and then this JNZ is checking if the accumulator is not 0. So if the register R1, which is moved to A, is not 0, then it goes to the next line, okay, which is denoted by this label. Otherwise, if it is 0, then it goes to the next line, which is moving 10 to R1. Okay. So this is kind of if-else type of logic that you use in high-level programming languages like C or Java or Python. So if it is not 0, then go to next line. If it is 0, then go to here. Okay. So this is a summary of different jump instructions that you can use, okay, and what they mean, and we will use them somewhere or the other when we practice assembly language coding throughout this semester. So we will see the use of these jump instructions. Okay. So I'll stop here for this lecture, and then I will see you in the next lecture.